Hi, everyone. Sorry this is getting out so late. One issue I was having is I was trying to decide whether to proceed directly to the central limit theorem or to spend some time doing at least one nice application of the weak law of large numbers. I think I've opted for the latter, namely going through an example involving the weak law of large numbers, because I think it will benefit you greatly. And I just really wish that someone, when I was learning probability theory for the first time, would have emphasized more emphatically the utility of things like Chebyshev's inequality and the weak law of large numbers. Okay, so let me go ahead and share this with you, and we'll get going. Okay. So a brief reminder of the various inequalities that we have. Okay, so that we have the Markov inequality, okay, which says that if x belonging to 0 to infinity is a random variable and a is just any number bigger than 0, then what's true? The probability that x is equal to or greater than a is less than or equal to the expected value of x divided by a. Okay, and that we use some indicator variables to come up with that. We even applied it in a couple of contexts. It's a very helpful inequality, but it really was Chebyshev that took this thing and pushed it to the next level. Okay, so let's write down the Chebyshev inequality. Okay, the Chebyshev inequality says here x is just a random variable. Okay, and we're going to write mu is the expected value of x, sigma squared equal to the expected value of x minus mu squared, i.e. the variance. Okay, and there are a few other things that we're really assuming here that I'm not writing down. For instance, I'm assuming that like the variance is finite, okay? But you know, that I guess in some ways it's not, we're not going to encounter those kinds of weird anomalies anyways. Okay, and then I'm gonna take k to be any number greater than 0. Then what? The probability that the absolute value of x minus the mean, so I'm looking at the difference between x and its mean, is greater than or equal to k, right? Is greater than or equal to k. Well, what is it? Is less than or equal to sigma squared over k squared. And remember, I mean, I really like to kind of think through the proof of this thing. The proof is like so trivial. Okay, so Markov, or hang on, let's just write this. The probability that x minus mu is equal to or greater than k. Well, that's obviously the same thing as the probability that that x minus mu squared is greater than or equal to k squared. Okay, and then I use Markov, right? So this step right here comes from Markov. Okay, is less than or equal to what? Well, I think of the x minus mu squared. That is my random variable. I think of a as being k squared. So it's less than or equal to the expected value of x minus mu squared divided by k squared, which is equal to sigma squared over k squared. Yeah? So the proof of Chebyshev really follows from Markov. And in fact, there's kind of like a higher degree version of Chebyshev. Sometimes, you know, you might call it the M-Chebyshev inequality. Okay, and I want to make a stipulation that M should really be even in order for this to work out. Okay, so this guy right here was like the 2 Chebyshev inequality. Okay, basically we look at the second power of x minus mu. Okay, so watch what this is going to say. Well, okay, I look at the probability that x minus mu, an absolute value, is equal to or greater than k. I am telling you this is the same thing as the probability. You just raise both sides to the m power, okay, where m is even. Okay, and what do I get here? X minus mu to the m greater than or equal to k to the m. And then I just invoke Markov again. Right? Markov again says that this is going to be the expected value of x minus mu raised to the m divided by k to the m. And believe me, I've found great utility for this higher degree version of the Chebyshev inequality. Okay, sometimes the Chebyshev inequality itself isn't good enough, but this guy oftentimes can give you precisely what you need. Okay, so hopefully that kind of makes sense. Well, what I wanted to do is to kind of revisit the law of large numbers. Remember, the law of large numbers, or the weak law of large numbers, okay, WLOLN, weak law of large numbers. What does the weak law of large numbers say? Well, it says that basically, if I have a bunch of IID random variables, okay, so x1 through xn, IID random variables, that means independent, identically distributed random variables. And remember, we used x bar to be the sample mean of these things. You just add them all together and divide by the total number of them. That's the thing you used to do in grade school. Yeah. Then, okay. Then for all epsilon greater than 0, what happens? Okay, so I fix an epsilon greater than 0, and I look at the probability that, oh, and by the way, we also observed the following. I just want to write this down too. Well, I'll just write down the conclusion and I'll mention this. The probability that x bar minus mu in absolute value is equal to or greater than epsilon, that this thing goes to 0 as n goes to infinity. Okay, and this is called convergence in probability. So x bar converges in probability to its mean. This is where I'll remind you what the mean of this thing is. To its mean, mu equal to the expected value of x bar. Okay, and I'll remind you that you know, we let mu is equal to the expected value of each of these xi's, but it also ends up being equal to the expected value of x bar. Okay, so x bar has the sample mean distribution, and the sample mean distribution has the same mean as the original data. Okay, and of course, if I write sigma squared equal to the variance of xi, we determined that that the variance of x bar is equal to sigma squared over n. And that observation was the key kind of to the proof of the weak law of large numbers. We ended up invoking the Chebyshev inequality. And so long as that variance was finite, again, that's one of the assumptions I'm kind of making here. So long as the variance is finite, you end up getting a bound that has like an n in the denominator, and that thing ends up going to 0. In fact, you know, the proof's kind of easy. It goes like this. Let's just actually prove it again real quick. Okay, so the probability that you know, x bar minus mu is equal to or greater than epsilon, okay, is less than or equal to, this is by Chebyshev. This is by the Chebyshev inequality, is less than or equal to what? Well, it's going to be less than or equal to the variance of x bar over epsilon squared. Okay, but this is just equal to sigma squared over n epsilon squared. And that goes to 0 as n goes to infinity. Okay, and this is, when you get deeper into probability theory, this stuff is called convergence in probability. But there are other ways that you can have convergence of one random variable to something, okay? The central limit theorem is going to be another version of convergence. It's going to be called convergence in distribution, okay? Which means that the probability distributions are getting closer and closer and closer as n gets larger. But this right here is called convergence in probability. There's also another kind of convergence called convergence almost surely. and that is like the version of convergence that is in the strong law of large numbers. It turns out that convergence almost surely implies convergence in probability. And so it's a stronger version of convergence, which is why this is called the weak law of large numbers. In some sense, convergence in probability is the weakest type of convergence in probability theory. Convergence in distribution and convergence almost surely are stronger versions of convergence, okay? But I wanted to do an example, all right? I mentioned, because the book really doesn't do any examples, they just kind of state the weak law of large numbers and like move on. But I think it's needful to at least look at an example so that we get a good feel for what's happening. Last time I mentioned, you know, some stuff about coin flips. And I said, this is why the larger the number of coin flips I do, I start to suspect that I'm going to have a proportion of heads for a fair coin that gets closer and closer and closer to 1/2. Closer and closer and closer to 1/2. Okay, so let's do that example. So let's do the example of the coin flip. Okay, so this is a fair coin flip. It's kind of the random experiment running in the background. And I'm going to let x equal to the number of heads in n flips. Okay, so I guess we're, oops, sorry guys. Okay, fair, so x is the number of heads, and I guess I'm doing coin flips here. Okay, this thing is going to have what kind of distribution? Well, it's going to be binomial with n trials in proportion of success 1/2. Right, so I'm keeping track explicitly of the number of heads. Okay, of course, you know very well at this point that the expected value of x is equal to np, which in this case is just n over 2. Okay, and what about the variance of x? That's npq. Or of course, q is just 1 minus p, and therefore this is just going to be n times 1/2 times 1/2, which is n over 4. Okay? And here's the question I want to answer. Okay, how many flips will guarantee a proportion of heads that is within 1/100th of 1/2 with probability greater than or equal to 99%. Okay? So within 1/100th of 1/2, that means, remember in the hundredths, so 1/2 is equal to 0.5. Okay? So within 1/100th, that means that it has to be, right, that it within 1/100th means it has to belong to 0.49 and 0.51. Now I want to know how many flips I have to do, right? The weak law of large numbers, I'm telling you right now, and I'm going to show you why. It guarantees that the proportion is going to get ever closer to 1/2 the larger the number of flips I do. And I want that to happen with probability greater than 99%. Okay, so first of all, I have to see this as a proportion of heads. Okay, notice that x over n is equal to the proportion of heads, right? N is the total number of flips, and x is the number of heads. So there it is. But I also want to see this as a sum of random variables, because the weak law of large numbers was a sum of things. Well, we know how to do that, right? So how do I write x as a sum? Well, I'm going to write x as the indicator, or as a sum of indicators, plus ... plus the indicator of hn. Where what do you think that these things are? Well, hi is equal to the event head on flip I. Okay, x is the sum of those indicators. Okay, then of course we have that x over n is equal to what? Well, it's 1 over n times the sum of these random variables. Okay, so that's starting to look a lot more like the weak law of large numbers. Okay, and I'm going to call this h bar. Okay, just so it kind of looks like what we were doing before. Okay, so this is the sample mean of proportion of heads, right? Okay, so this is kind of the sample mean in this particular case. Okay, of course, what is the expected value of h bar? Well, that's easy because that's just x over, right? The expected value of x is n p, or n over 2. I just have to divide that by n. So the expected value of this thing is 1/2. Okay. What about the variance of this thing? What is the variance of h bar? Well, okay, h bar is basically 1 over n times x. So isn't that just going to be 1 over n squared? Right? Because 1 over n, when I factor it out, it's going to be 1 over n squared. It's going to be 1 over n squared times the variance of x. Okay? And you know the variance of x is n over 4. So that's just 1 over 4n. Okay? 1 divided by 4n. Okay, 1 divided by 4n for that particular thing. Okay, so I have all this stuff. I have my h bar, which is the proportion of heads. Okay, I know what the expectation of this thing is. I have the variance sitting right there, etc. Right? So what I'm going to do, I mean, look, I know that the weak law of large numbers says that the probability of being equal to or greater than any particular epsilon is going to be less than or it's going to go to 0, okay? But I wanted a very specific epsilon in this case. Okay, so really it's not so much the weak law of large numbers that I'm applying, it's just the idea behind it, namely the Chebyshev inequality. Okay, so let me just say the weak law of large numbers, and I'll just say really Chebyshev implies what? Okay, well, the probability of H bar, not X bar, H bar, which is the proportion of heads, minus a half, that's its mean, being greater than or equal to, okay, this time, what did I want? You know, I wanted this thing to be within 1/100th of the thing, okay? So this is 1 over 100. Okay, this is less than or equal to the variance of H bar over 1 over 100 squared. That's by the Chebyshev inequality. Okay? 1 over 100 squared, which is equal to 100 squared times the variance of H bar. Which, by the way, is equal to what's variance of H bar? That's 1 over 4n, right? By the way, 100 squared is 10,000. Okay, this guy right here is 1 over 4n. Okay, so if I take 10,000 and divide it by 4, that's like 2,500 over n. 2,500 over the number of flips. Okay, so that's interesting. So let's kind of think about this for a minute. Okay, this guy right here is this thing right here. If you think about it for a second, the left-hand side, that's the same thing as 1 minus the probability that what? The proportion of heads minus a half is less than 1/100th, which is kind of what I wanted. I wanted this thing to be within 100th of its mean. Yes? So this thing is less than or equal to, right? It's the same thing over here, 2,500 over n. Okay? 2,500 over n. So what does that mean? That means that the probability that H bar minus a half, right, that proportion is within 100th of its mean, 1/2, is greater than or equal to 1 minus 2,500 over n. Okay? And what did we say we wanted? We wanted that to happen with probability at least 99%. So I wanted this to be greater than or equal to 0.99. Okay, well, let me just say 99 out of 100. Okay, well, what does that mean? Okay, so let's kind of stare at this. So I want this to be bigger than or equal to 99 over 100. Let's stare at this for just a minute and kind of think about it together. Okay, so that would mean that if I subtract 99 over 100 over from 1, okay, that would be 1 over 100 would need to be greater than or equal to 2,500 over n. Okay, which means that n would need to be greater than or equal to, okay, I need to cross multiply through, n would need to be greater than or equal to 250,000, 250,000. Okay. Okay. So what this means is the weak law of large numbers under the guidance of the Chebyshev inequality guarantees that if I were to flip a coin 250,000 times, there is a 99% chance that I'm going to be within 100th of the mean 1/2 in terms of proportion of heads. Okay, so that means I'm going to fall within the range 0.49 to 0.51 with 99% probability. Okay, now I want to show you one more thing here, and I'm going to be done. It's a little simulation. Okay, it's pretty cool. All right, so I'll pause this and we'll go check that out. Okay, so here I am over here on the internet. This is a GeoGebra simulation. There are plenty of simulations. This one's particularly interesting though. So if you want to kind of watch what we've just been talking about play out over time, there's like a relative frequency of heads situation. And what you do is you just kind of run the simulation, and this thing will keep track of the number of heads, and it gives you the relative frequency of heads. In this particular simulation that I was messing with yesterday, you can see that I let this thing do 236 flips. There were 130 heads and 106 tails, and the relative frequency of heads was 0.551. But remember, we just proved that that would be extremely unlikely that the relative frequency of heads would be that high if we were to flip the coin 250,000 times. Okay, that indeed there's a 99% chance that we would be between 0.49 and 0.51. Okay, so let's go ahead and run this thing. I'll just kind of show you how it evolves over time. Okay, so this thing's moving pretty slow right now, but you could actually speed it up. Do you see what it's doing? It's kind of tracking the blues, the number of heads, the green is the number of tails. Down here, it's like, this is the percentage of heads that's going on. Okay, the tails is now kind of caught up at this point, and you could like speed this thing up. Okay, see this? And it kind of self-adjusts as time goes on a little bit. It's a pretty cool little thing, right? Yesterday, I didn't actually let this thing run to 250,000. I think I was able to get it to several thousand though, and it was already starting to settle down into the right range. But you see how you have all this random noise at the beginning, and you can see that this thing is really starting to hunker down, and it doesn't have all these you know, ridiculous fluctuations like it did at the beginning. Okay, that's kind of an indication that the sample mean statistic, the sample mean distribution is much more better behaved. It's not as prone to random fluctuations because big values and small values tend to balance each other out. So you tend to hunker down around the mean more. And the weak law of large numbers is a very precise articulation of that fact. Okay, so you can kind of see, look, heads is just destroying tails right now by 27 or 28, but we know that eventually, at least the proportion of heads has got to dip lower than it is right now. Okay, you can go check that out on GeoGebra. There's lots of other simulations as well, rolling die, flipping multiple coins. So there's some pretty cool simulations you can run in GeoGebra in relationship to simulations of coins and dice. There's some other ones as well that are sort of interesting, and some of them have cool, like you can like pick the kind of coin you want to see, like a buffalo head nickel or whatever. Okay, all right, I'm going to leave it at that for now. On Monday I will actually prove the central limit theorem for sure, and we will have a homework quiz next week. I don't expect that it's going to be any different than any other typical homework quiz, but just so that you have something from this class to work on and just to bolster the number of homework quizzes that you have on file right now. All right, that's all I have. I hope you have a good weekend, and I'll see you later.